Hey everyone, welcome to The Explainer. There's this kind of fascinating and honestly a bit scary paradox in software development. Think about it. The more helpful and detailed an error message is to a developer, the more incredibly helpful it is to an attacker, right? It seems like a super basic programming topic, but error handling is actually one of the most commonly mismanaged aspects of application code out there. Every single error message you display to a legitimate user is also being served right up to attackers. So the big question we're answering today is exactly how much of your system's blueprint are you just handing over to them? Here's our roadmap for today. We're going to start with a high-level look at the actual threat model. Then we'll hit the core fail securely principle, dive into smart authentication, and then jump straight into actionable code-level fixes by language. We'll wrap the whole thing up with HTTP status codes and a definitive secure developer checklist. All right, Section 1, the threat, and why errors are basically reconnaissance gold. So OWASP, the Open Web Application Security Project, actually categorizes verbose errors under insecure design for a very good reason. If we compare a dangerous error message, like a massive, detailed stack trace, with a secure one, the difference is wild. To a developer, that stack trace is great for debugging, but to an attacker, it is a literal treasure map. The secure approach, on the other hand, is just a generic message like an unexpected error occurred, paired with a reference ID. It gives the user context, but it gives the attacker absolutely nothing to work with. All those little details in a stack trace built into what we call a tech stack fingerprint. Seriously, look at what an attacker can extract from just one bad error. File paths reveal your exact directory structure. Framework versions tell them exactly which known vulnerabilities, which CVEs to go try. Database errors can literally expose your internal schema, like missing columns. You are essentially handing over a detailed architectural blueprint of the very walls they are trying to break down. No way we want to do that. Moving on to Section 2. The fail securely principle. Here's the thing. As a developer, you absolutely do not have to sacrifice visibility for security, as long as you follow one core philosophy. Default to denying information, not exposing it. When an error happens, your app should immediately default to a safe state. All that juicy, detailed info, that goes straight to your internal servers and is completely 100% denied to the end user. So how do we actually build this out? It's all about the reference ID pattern. It's a simple 3-step blueprint. Step 1, generate a unique identifier like a UUID for the error. Step 2, log the full detailed error server side and attach it to that UUID. Step 3, show the user a generic message with just that ID, something like ERR-7A3F. Boom. You get full traceability for your support team, and the attacker gets a completely meaningless string of characters. It's a win-win. Section 3. Smart Authentication Error Handling. Login endpoints are, without a doubt, the most heavily targeted areas of literally any application. Edge cases here matter so much. Think about those classic error messages we've all seen. User not found or incorrect password. Why are these actually terrible? Because you must never reveal which part of the authentication process failed. Giving specifics allows attackers to easily enumerate valid accounts or kick off brute force attacks. The secure response is always a completely generic, invalid username or password, no matter what actually went wrong behind the scenes. But wait, there is a super sneaky, hidden danger here, even if your text is perfectly generic. Timing attacks. Your system's response time absolutely must be identical whether the user exists or not. Think about it. If it takes 10 milliseconds to reject a fake user, but 200 milliseconds to reject a real one because of database lookups, an attacker can map out your valid users just by using a stopwatch. They completely bypass your secure error text. Okay, Section 4, Secure Coding by Language. Let's do a really quick, rapid-fire rundown of some practical implementations. First up, Python developers using Flask. You want to use logger.exception for internal logs and return a JSON response with your UUID. But the absolute most crucial point, Flask debug must be set to false in production. Leaving debug mode on is a catastrophic mistake because it literally exposes a fully interactive Python debugger to anyone who triggers an error. Yeah, let's definitely not do that. Now for you JavaScript devs using Express, you need a global error handler middleware. Log the error internally, but never, ever pass error.message down to the client. Also, make sure you set node.env to production, which automatically stops Express from sending stack traces. And remember, because Express executes sequentially, your error handler needs to be the absolute last piece of middleware you register to catch everything. And over in Java land with Spring Boot, you'll use @controller advice to create a global exception handler and @exception handler for specific errors. You log the exception using SLF4J, making sure to include a correlation ID, and then return a generic response entity. Critically though, in your Spring Boot properties, set server.error.include stack trace to never. This completely stops Spring's default error page from leaking stack traces for any random exceptions your custom handler might have accidentally missed. Section 5. HTTP status codes done right. Secure error handling isn't just about the text itself, it's about guiding clients securely with the right HTTP status codes. 400 is for bad input, 401 means unauthenticated, 403 is forbidden. Now, I want you to pay special attention to the nuance between 404 and 403. For authenticated endpoints, you should actually often return a 404 not found instead of a 403 forbidden. Why? Because throwing a 403 confirms to the attacker that the hidden resource actually exists. And finally, a 500 is for internal server errors, which, as we know, must always be paired with a totally generic message. All right, Section 6, the Secure Developer Checklist. Let's wrap this up. Let's bring this all together. Here are your absolute non-negotiable takeaways. Never expose stack traces to users. Just don't do it. Always log detailed errors server-side using the reference ID pattern. Reveal absolutely nothing specific in authentication errors. Ensure debug mode is off in all production environments. And finally, always use global error handlers as your safety net. Error handling is all about not handing over your application's blueprint. Okay, quick quiz time to see if you're tracking with me. Why should authentication errors never specify whether the username or password was incorrect? Think about it for just a second. Well, it's to prevent attackers from enumerating valid accounts. If you tell them the email exists, they can immediately pivot and begin brute forcing the password. And question 2, what setting must absolutely positively be disabled in Flask or Django production environments to prevent exposing an interactive debugger? You guessed it, debug mode. It must be turned off. This actually brings us to a final pretty provocative thought to leave you with today. We've just spent this entire explainer making sure you've locked down and secured the errors you display to the user. But are you prepared for the fact that what you log server-side might be just as dangerous if it falls into the wrong hands? If an attacker gets your logs, do they get your passwords? Something to seriously think about. Thanks for joining me on this explainer, and keep your code secure.